welcome to Acids video number 3. We're going to talk about indicators, neutralization, and titration. And here we go. What are indicators? Indicators are chemicals that change color in different pHs. They're usually weak acids, but the key is they're one color in the acidic form and they're another color in the base form, meaning after they've lost their hydrogen ion. So there's this little relationship there. We have the intact acid, and then since it's a weak acid, not much of this happens, but when it does lose its hydrogen ion, the indicator anions, what's left, is a different color. So these help us find approximate pH. They're limited by the fact that they're subjective in color. Ranges are narrow, so there's really no sig figs, and the colors can fade and mix. So this is a table of common indicators. What I'm going to ask you to be responsible for are these three: phenolphthalein, bromethymol blue, and methyl red. We already know litmus from the properties of acids and bases, so that one we know. But methyl red, bromethymol blue, and phenolphthalein are the most common. We'll encounter them in class also and in lab. So we're going to be looking at these values. So we're going to have a certain color, and that color will tell us something about the solution. We're going to use a combination of them to determine the pH of a solution, like the one here. It says identify the pH of the substances that turn the following colors in presence of listed indicators. Use a number line, and look, we have a number line. So when phenolphthalein is color, let's look back. We see that colorless is less than 8.2, and so I'm going to slide this pink one to where it has less than 8.2. So that means the range of 0 to 8.2s are possible if we just know phenolphthalein. But if we know that methyl red is yellow, that's a pH of greater than 6.2. So we'll slide that this way. And then finally, bromethymol blue is blue, BTB. Don't get that confused with bromcresol green or another similar. When it's blue, it's greater than 7.6. So we'll slide this all the way to about there. And so I'm going to fill in some gaps here with actual numbers so we can get a good range. We know that that's greater than 8.2 according to phenolphthalein, or sorry, less than 8.2 according to phenolphthalein. We know that it is greater than 6.2 for methyl red and greater than 7.6 for bromethymol blue. And so this narrow range is where our pH lies. And ultimately it is going to be greater than 7.6 and less than 8.2. That would be how we would respond. Identify the pH of the substances based on these values. We have phenolphthalein is colorless again, so we can just drag that into place. Less than 8.2. And then methyl red is red. Let's see what that means. Methyl red is red is pH of less than 4.4. And then bromethymol blue is yellow. When it's yellow, BTB is yellow is less than 6.0. Write that there. So again, less than 6.0, less than 4.4, less than 8.2. So the best we can do is this range here, 0 to 4.4, less than 4.4 really, but that's a good enough range. So you see how indicators can give you a decent idea of where your pH of your solution lies. Neutralization is the next big concept. We're going to use this in the upcoming ideas we're going to talk about, but this is a refresher. You guys already know what neutralization is. Acids and base make water into salt, and that salt is made from the anion from our acid and the cation from our base. And we're going to need to understand that these have to be balanced to work in titration that we're about to talk about. So the only one I'm going to draw right now is this one. Let me clear that out for you, and then we'll write it again together. Nitric acid, HNO3, reacts with potassium hydroxide to form water and the salt potassium nitrate. Potassium and nitrate are both 1 charges, so it's KNO3, and so to balance we simply will have 1s. Just to bring back net ionic equation, keep in mind in net ionic equation we write down everything that's not a spectator, and we should know from our solubility rules by now that nitrate's always soluble and so is potassium, so those just go away, and that's going to leave us with hydrogen ion, hydroxide ion making water. That is the net ionic equation of any strong acid, strong base neutralization. So we'll keep in mind we're going to have to balance these reactions for the rest of the unit, all right? So let's look at the next one. Titration is a process in which neutralization reactions are used to determine the molarity of an unknown solution. Now, generally speaking, this is not always true. When you titrate, you have a burette, or some other mechanism to dropwise slowly by small volumes add to an unknown acid or base um, to determine the concentration. And we're taking advantage of neutralization when we do this, because we know that if our solution of acids and bases have equal number of moles of acid and base, then we will have a neutral solution, theoretically. Okay, so when a strong acid, strong base react together, if we put them in exactly stoichiometric amounts, it leaves us only with salt and water. And it should have a pH that's predictable around 7. Okay? Um, so this is a burette. Again, the titrant is what you're titrating with. Usually, you will see sometimes people will titrate with your analyte, but generally speaking, in the lab, this is the way it's done. So uh, the known solution is titrated into the analyte very slowly, and you're trying to look for either a color change using an indicator, or you can use a pH meter to watch for pH changes. Okay, you can collect data. There's all sorts of things you can do in titration. Additionally, titrations aren't only used in acid-base reactions. They're also used in other types of reactions where there's an unknown you're trying to calculate. In a titration, you're looking for equivalence, which is where you have equal moles of acid and base, hydrogen and hydroxide. And that's going to be what's considered, quote, your neutral solution, all right? We use indicators that change color at certain points. That indicator changes is called its endpoint. So endpoint has to do with an indicator, okay? Keep that in mind. A lot of people get that confused with equivalence. An indicator changing color is endpoint. Your job as a student and a scientist is to choose your indicator that's going to change colors or have an endpoint when you reach equivalence. Okay, and we'll talk about that when we actually look at some titration curves in a moment. When you choose an indicator, you want endpoint to be as close as equivalence as you can. Now, there's not necessarily perfect, but when we do titrations and we look at the data, we'll see why that there's an acceptable range when choosing indicators. So this is a strong acid. Notice our pH at the beginning is less than 2 and being titrated by a strong base. The base is being dripped in. You see the pH slowly changing, and then we see a point at which we get very close to equivalence, which is here at 7. That's where we have equal moles of acids and base. And we see this almost a vertical rise. And this is just a matter of a few drops here, going from here to here, just a few drops. So look at that. Really and truly, you can use most indicators for a strong titration. All right. The reason is that this is such a small difference in volume that this indicator changing color and this one are so close to the proper volume that by sig figs you're going to be about right. Okay, so in a strong titration, there's a large range of indicators you can choose to find equivalence. Now, are they perfectly having an endpoint on equivalence? No, but they're both very close. So there are other indicators that do have a nice endpoint right around 7. So don't think these are the only two. We can always choose based on the information we have. Notice on strong, you have less than 2 for my acid, and then ending at greater than 12. Okay, generally speaking, this is a trend you'll see is a nice flat curve, a vertical rise, and another flat curve, starting at the extreme and ending at the other extreme. When you start with a weak acid, notice that your curve starts a little higher, above 2. Notice also that there's a curve where you kind of start off with a pretty significant slope, and then it flattens out, and then we have our vertical a little higher. Notice our endpoint for a weak acid being titrated with a strong base is higher than 7. And it has to do with a strong base, and we'll talk more about that in AP. But the big idea here is that we can recognize this curve type as a weak acid being titrated by a strong base. Notice that we end up at the same point up here as we did in our other titration because we were using a strong base as our titrant. Strong base being titrated by a strong acid, you should note that we're starting with a base this time, okay? The base has acid dripped in. We have a nice high pH. It's going to be almost a vertical drop again, and then we're finishing with a very low pH. So it's just a reverse. You know, this since it's done left to right by volume added, you should always be able to determine this is an acid, or sorry, a base being titrated by an acid, okay? So please keep that in mind. It's written literally. A strong base titrated with a strong acid. Here we have a weak base being titrated with a strong acid. Our pH finishes up about 2, but notice we start out less than 12, and there's a curve to start us off, a nice flat region where it's not much has changed. It's called a buffer region. This is more of an AP topic, but you see that flat area there, and then we have our nice, big, long, straight equivalence zone, and equivalence of less than 7 when there is a weak base and strong acid. Again, the strong acid is the reason that our pH is less than 7 when you titrate a weak base and a strong acid. Let's compare, just for the sake of understanding the difference in the curves. Now, these are very dramatic, okay? They're not always going to be quite this dramatic, but the big idea is that in a strong titration, you have a nice low or high pH to start off, and it's flat, and then a long equivalence zone, and then it ends off flat again. When there's a weak acid, notice that we start with a little bit of a slope, and then it flattens out. Our equivalence is higher than 7 when it's a weak acid, strong base. And when it's a weak base, strong acid, our equivalence is less than 7. So use these two comparisons to help you understand the differences in the titration curves of these two different scenarios. In titration calculations, we're going to be using the math we already understand through dimensional analysis to find out the molarity of an unknown, okay? We've already introduced this idea, so I'm going to quickly just talk you through the terms I'm going to use. First, we have to have a balanced reaction. We're going to need mole ratio to make this right. We're going to write the known quantities below our reactants, and then we're going to use stoichiometric analysis to find that volume. We're going to start with the volume of the titrant in liters. Keep in mind we're often going to be working with milliliters, and so if we have 30 milliliters, that's just going to be in liters, 3 to the left, and so you'll see me quite quickly go from 30 mils to 0.030 liters. If you want to do it literally, you can say 30 milliliters, 1,000 mils is 1 liter, and the dimensional analysis should give you 0.030. But you'll see me rather quickly do this momentarily. So first things start with the volume of the titrant, and then we're going to use the molarity of the titrant to find the moles of the titrant, and we're going to use mole ratio to convert that to the analyte, and then solve for concentration by dividing by the volume of the analyte. But this makes more sense when we talk it through. So here we go. 25 mils of 1 molar potassium hydroxide are added to 46 mils of an unknown molar hydrochloric acid solution. So I urge you immediately to recognize your titrant's the thing you have a volume and a molarity of, and your analyte's the thing that has an unknown value. We're going to write our reaction. We have hydrochloric acid and potassium hydroxide, and you should realize pretty quickly here that this is a 1-to-1 ratio, because we're going to make 1 water, H2 and O, and we're going to make charges of +1, -1, KCl. And so our coefficients are 1, 1, 1, 1. How fun is that? Remember I said that we're going to begin with the volume of the titrant, the thing we have all the information about. And I'm going to convert that to a volume of 0.025 liters. And then we're going to use molarity to convert this liters to moles. I know that we have 1 mole per 1 liter of KOH. So that liters cancels, and now I have moles. Then I can use mole ratio to go to hydrochloric acid. 1 mole KOH is 1 mole of hydrochloric acid. And then I'm just going to divide by the volume of my titrant in liters, 0.0464 liters. And that's going to give me our answer, 0.025. And those are all ones, so divided by 0.464. And I get 0.538793, and drag this out, and there we have it. 0.539 molar hydrochloric acid, 3 sig figs, because all the values I began with had 3 sig figs. And there we go. And then we have a 25 ml solution of sulfurous acid, strong or weak, people? Right, it's weak. Of unknown molarity is completely neutralized by 18 milliliters of 1 molar sodium hydroxide. Now, this is a neutralization reaction. Titration is for neutralization. It's also for examining titration curves, and we will do both. But we just neutralized, in this question, 25 mils of an unknown with 18 mils of a known base of 1 molar. So we're going to start with the volume of our titrant. Which one's our titrant? Which one is our titrant? It's the thing we have all the information about, the molarity and volume. There's our titrant, and our analyte is our acid. First, though, we must have a reaction. Sodium sulfite. So sulfite's -2, so it's going to be Na2SO3. Then to balance, notice we've got 2 sodium, so there's going to be a 2 here, a 1 here, a 2 there, and a 1 there. So we have a 1-to-2 ratio of acid to base. That's hugely important. So to start off, volume of the titrant, 0.018 liters. The molarity of the titrant, 1.0. And then our conversion. For every 2 moles sodium hydroxide, 1 mole sulfurous acid. Moles cancel, liters cancel. And then all we do at that point is divide by the volume of our analyte, 0.025 liters. Our calculator, 0.18 times 1 divided by 2, then divided by 0.025. And then we get 0.36. Now how many sig figs do we have here? 3, 2, 2. So 2 sig figs should be in my answer. There's our balanced reaction, and our answer is 0.36 molar sulfurous acid. There's an additional question here. It says, what's the pH of the titrant? Our titrant was sodium hydroxide 1 molar. How do we find the pH of that? Well, we do negative log. Negative log. Oop, I didn't mean to graph. Escape. Negative log 1, right? 1 molar. Our pH is 0. Is that okay? Yes, it's just fine. Typically, when we have strong acids, strong bases with molarities of 1 and greater, we see pHs of 0. When molarity is greater than 1, we can actually have negative pHs, and that's okay. All you're doing is negative log of a value, and if it comes out negative, it comes out negative. So, this concludes Acids 3, Indicators, Neutralization, and Titration. You need to make sure you've gone through with high-quality notes on this. I would have drawn every single titration curve type, pointing out the details that differentiate them. Rewatch any portion of this video you feel is necessary, and please make sure you've written down your questions and come to class ready to ask.